Welcome! In this session, we will explore LeetCode problem number 632, titled Smallest Range Covering Elements from K-Lists. This is a fascinating problem that challenges us to identify the smallest range covering at least one element from each of several sorted lists. We'll break down the problem, discuss approaches, and analyze its complexity. Let's get started. In this problem, we are tasked with finding the smallest range that includes at least one number from each of the given lists. You are provided with K-lists of sorted integers, where each list is guaranteed to have at least one element. The goal is to determine a range, left, right, such that every list contributes at least one number that falls within this range. If there are multiple ranges of the same length that satisfy this condition, we prioritize the one with the smallest starting value, left. The input consists of a list of these sorted lists, and the output is a pair of integers, left, right, representing the smallest range. This problem challenges us to efficiently analyze the overlap and distribution of elements across multiple sorted sequences. Let's dive into an example to understand the problem better. Suppose the input consists of three lists, 4, 10, 15, 24, 26, 0, 9, 12, 20, and 5, 18, 22, 30. The output for this case is 20, 24. Why? Because the range, 20, 24, includes at least one number from each list. From the first list, the number 24 is within this range. From the second list, the number 20 is included, and from the third list, the number 22 is included. This range of 20, 24 is the smallest possible range that satisfies the condition. Any smaller range would fail to include at least one number from all three lists. Now, let's look at another example where the input lists are simpler. Consider three lists, each containing 1, 2, 3. In this case, the smallest range that includes at least one number from each list is 1, 1. Here, the number 1 from all three lists satisfies the condition, and no smaller range exists. This example highlights how the solution must adapt to cases where all input lists are identical or overlap entirely. Additionally, for an input like 10, 10, 11, 11, the smallest range would be 10, 11. The number 10 comes from the first list, and 11 comes from the second list, forming the smallest range that includes a number from each list. To elaborate on the constraints, the problem allows for a wide range of possibilities. The number of lists, k, can be as small as 1 and as large as 3500. Each list can contain between 1 and 50 integers. The integers themselves can range from -10⁻5 to 10⁻5. All lists are guaranteed to be sorted in ascending order, and no list is empty. These constraints imply that the solution must be efficient enough to handle up to 3,500 lists while processing elements that span a wide numerical range. The algorithm must also handle cases where the input lists are highly unbalanced in size or contain overlapping ranges. Finally, let's consider some edge cases that the solution must handle. If there is only one list, the smallest range is simply the range of that list. When the input lists have varying lengths, the algorithm must still identify the correct range efficiently. For inputs containing very large or very small numbers, the solution must handle the full range of values without encountering overflow or precision issues. Additionally, overlapping ranges across different lists must be accounted for, ensuring that all lists contribute to the final range. Whether k is small or large, the algorithm must perform efficiently, adapting seamlessly to the scale of the input. When solving this problem, our goal is to find the smallest range, left, right, such that at least one number is included from each of the k-sorted lists. Initially, we might consider a brute force approach. This involves generating all possible ranges, left, right, that include at least one number from each list, and then checking if the range satisfies the condition. The smallest valid range would then be tracked as the result. However, the computational cost of this method is prohibitive. Since we would need to iterate over all possible combinations of k-lists, the complexity grows exponentially, approximately n to the power of k, where n is the total number of elements across all lists. While this approach is conceptually simple, it quickly becomes impractical for larger inputs, making it unsuitable for real-world scenarios. To address the inefficiency of brute force, we use an optimized approach that leverages the sorted nature of the lists. The key idea is to maintain a sliding window that dynamically includes at least one number from each list, while tracking the smallest range. This is achieved using a min heap, which helps us efficiently manage the smallest element in the current window. We begin by inserting the first element of each list into the heap and tracking the maximum element in the window. As we process elements, we continuously pop the smallest element from the heap, move to the next element in the corresponding list, and update the window. The process stops when any list is exhausted, as we can no longer include all lists. This approach reduces the complexity significantly. Since heap operations like insertion and deletion take O log k, and each element is processed once, the overall time complexity is O n log k. While this method requires additional space for the heap and careful handling of list pointers, it is highly efficient for large inputs and avoids the pitfalls of the brute force approach. The success of this approach is rooted in a few key observations. Since each list is already sorted, we don't need to consider every combination of elements. Instead, focusing on the smallest and largest elements in the current window allows us to dynamically manage the range. The use of a heap is crucial here. It lets us efficiently track the smallest element in the window while separately keeping track of the largest. This ensures that the range is updated optimally at every step. The sliding window with a min heap is chosen because it balances efficiency, simplicity, and optimality. With a time complexity of O n log k, this method is scalable even for large inputs. Although heap operations introduce some computational overhead and additional memory usage, these trade-offs are minor compared to the exponential growth avoided by this approach. Overall, this strategy guarantees the smallest valid range by systematically iterating through all possible valid windows in an efficient manner. In this problem, we are given k-sorted integer lists, and the goal is to find the smallest range, left, right, such that at least one number is chosen from each of the k lists. The range should be as small as possible, and if there are multiple ranges with the same size, any valid range can be chosen. To solve this, we use a combination of a min heap and a sliding window technique. The min heap helps us efficiently track the smallest element across the lists, while the sliding window ensures that we cover all k lists within the range. Let's break this algorithm down step by step. The first step is initialization. We create a min heap to store the smallest elements from the lists. Each entry in the heap is a tuple, value, row_index, col_index, where value represents the current number, row_index identifies which list the number comes from, and col_index indicates its position in the list. To calculate the range, we also maintain a variable current_max to track the maximum value among the elements in the heap. Next, we push the first element of each list into the heap. As we do this, we update current_max to ensure it always reflects the maximum value among the elements currently in the heap. Once the heap is initialized, we move to the sliding window process. While the heap is not empty, we extract the smallest element from the heap, which gives us the left boundary of the current range. Using this, we compute the range, min_value, current_max. If this range is smaller than the best range found so far, we update our result. To move forward, we push the next element from the same list into the heap, using the row_index and col_index of the extracted element. If the new element is larger than current_max, we update current_max. However, if there are no more elements in the list, the process stops because it becomes impossible to cover all k lists in the range. This approach relies on key insights to ensure efficiency. First, the min heap allows us to track the smallest element in the current window efficiently, enabling us to expand the range only when necessary. The range at any step is determined by the smallest element in the heap, which acts as the left boundary, and current_max, which acts as the right boundary. This guarantees that all lists are represented in the range. Additionally, the algorithm terminates early as soon as any list is exhausted, as extending the range further would no longer satisfy the problem's constraints. Using these principles, we achieve an optimal and systematic solution to the problem. Now let's analyze the complexity of this algorithm. For time complexity, heap operations such as push and pop take O log k time. Since each element is pushed and popped from the heap exactly once, the total time complexity is O n log k, where n is the total number of elements across all lists. For space complexity, the heap stores at most k elements at any time, resulting in OK space usage. To bring this to life, consider an example with the input lists 4, 10, 15, 1, 12, 20, 7, 8, 30. Initially, we push the first element from each list into the heap, resulting in 1, 1, 0, 4, 0, 0, 7, 2, 0, with current_max set to 7. From the initial heap, we extract the smallest element, which is 1. This gives us the range 1, 7. Next, we push the next element from list 1, which is 12, into the heap. The heap becomes 4, 0, 0, 7, 2, 0, 12, 1, 1, and current_max is updated to 12. We then extract 4, updating the range to 4, 12. The next element from list 0, which is 10, is pushed into the heap, resulting in 7, 2, 0, 12, 1, 1, 10, 0, 1. This process continues until we exhaust one of the lists. In this example, the smallest range that covers at least one element from each list is 7, 12. In this implementation, we start by importing the heap module, which will help us manage a min heap. The goal is to maintain a window of elements across the lists that ensures we cover at least one element from each list while keeping the range as small as possible. Inside the smallest range function, we first initialize an empty min heap and set max_value to -infinity. This max_value tracks the largest element in our current window, helping us calculate the range dynamically. Next, we initialize the heap by pushing the first element of each list into it. Each entry in the heap is a tuple containing the value, the index of the list it comes from, and the index of the element within that list. At the same time, we update max_value to ensure it reflects the largest value among the first elements of all lists. Now, we prepare to process the heap. Before doing so, we initialize a variable called smallest_range with infinite bounds, which will later hold the optimal range. The while loop begins, and it will keep running as long as the heap has elements. Within the loop, we pop the smallest element from the heap. This element represents the minimum value of the current window. We then calculate if the range from min_value to max_value is smaller than the current smallest_range. If it is, we update smallest_range. After that, we attempt to move to the next element in the same list as the one we just popped. If another element exists in that list, we push it onto the heap, ensuring the heap always reflects the smallest available elements across all lists. Once the next element from the same list is pushed onto the heap, we update max_value to ensure it reflects the largest value in the current window, as this is necessary for calculating the range. However, if there are no more elements in the current list, we break out of the loop. This is because it is no longer possible to cover all lists, and any further calculations would be invalid. The loop ensures that we systematically update the heap and evaluate the range at each step until one of the lists is exhausted. Finally, once the loop terminates, we return smallest_range, which holds the smallest range that includes at least one number from each list. This implementation efficiently narrows down the range using a min heap, ensuring we always maintain the smallest possible window while iterating through the lists. Here, we begin with the Java implementation of the problem. The goal is to find the smallest range that includes at least one number from each of the given lists. To achieve this, we use a min heap, implemented with a priority queue, to track the smallest elements within the current window. The comparator ensures that the heap is sorted based on the values of the elements. We also maintain a variable, maxValue, to track the maximum value in the current window as we process the lists. Initially, we populate the heap with the first element of each list. Each entry in the heap is a triplet containing the value, the index of the list it belongs to, and the index of the element within that list. As we do this, we update maxValue to be the maximum value among these first elements. Then, we define two variables, start and end, to keep track of the smallest range we find. The main loop begins, where we continue processing the heap until one of the lists is fully traversed. Inside the loop, we extract the smallest element from the heap, which gives us the current minimum value, and record the associated list and element indices. Now, we check whether the range formed by the current max value and min value is smaller than the previously recorded range. If it is, we update start and end to reflect this new range. Next, we attempt to move forward in the list from which the current minimum value was extracted. If there is a next element in that list, we add it to the heap, updating max value if this new value is greater than the current max value. However, if the list is exhausted and there are no more elements to process, we break out of the loop since we can no longer cover all lists. Finally, once the loop ends, we return the smallest range as an array containing start and end. This ensures we've efficiently found the smallest range covering at least one number from each list using the properties of the min heap and careful tracking of the maximum value in the current window. We begin with the input lists nums equals 1 2 3 4 5 6 7 8 9. The first step is to initialize a min heap to efficiently track the smallest elements across all lists and a max_value variable to record the largest element in the current range. Initially, we push the first element from each list into the heap, resulting in tuples 1 0 0, 4 1 0, and 7 2 0. The heap now contains these values, and we compute the initial max_value as the maximum of the first elements, max 1 4 7, which equals 7. This setup ensures we have both the smallest and largest values at our disposal to calculate the first range. In the first iteration, we pop the smallest value, 1 0 0, from the heap. This gives us a current range of 1 7, which we record as the initial smallest range. Next, we push the next element from list 0 2 0 1 into the heap and update max_value, which remains 7 since max 7 2 is still 7. The heap is now restructured to maintain order, resulting in 2 0 1 7 2 0 4 1 0. In the second iteration, we pop 2 0 1 from the heap. This represents the next smallest value, giving us a new range, 2 7. Since this range is still valid and smaller than the previous one, we update smallest_range to 2 7. Then, we push the next element from list 0 3 0 2 into the heap. The max_value remains 7 as max 7 3 does not change. The heap now contains 3 0 2 7 2 0 4 1 0. In the third iteration, we pop 3 0 2 from the heap, leading to a new range, 3 7. As this range is smaller than the previous one, we update smallest_range to 3 7. At this point, list 0 is exhausted since there are no more elements to push into the heap. With one list fully processed, we terminate the algorithm, and the output for this example is 3 7. Now, consider the input nums equals 1 3 5 10 12 4 6 8. As before, we initialize the heap by pushing the first element from each list, 1 0 0, 10 1 0, and 4 2 0. The max_value is calculated as max 1 10 4, which equals 10. This gives us a heap of 1 0 0, 10 1 0, 4 2 0. In the first iteration, we pop 1 0 0 from the heap. The smallest value is 1, and the current range is 1 10. We update smallest_range to 1 10. Next, we push 3 0 1 into the heap, the next element from list 0. The max_value remains 10 since max 10 3 is still 10. The heap now contains 3 0 1 10 1 0 4 2 0. In the second iteration, we pop 3 0 1 from the heap. The smallest value is now 3, resulting in a new range, 3 10. We update smallest_range to 3 10. Then, we push 5 0 2 into the heap, the next element from list 0. The max_value remains unchanged at 10. The heap is now 4 2 0, 10 1 0, 5 0 2. In the third iteration, we pop 4 2 0 from the heap. The smallest value is 4, giving us a new range, 4 10. We update smallest_range to 4 10. The next element from list 2 6 2 1 is pushed into the heap, and max_value remains 10. The heap now contains 5 0 2, 10 1 0, 6 2 1. In the fourth iteration, we pop 5 0 2 from the heap. The smallest value is now 5, resulting in a range, 5 10. We update smallest_range to 5 10. At this point, list 0 is exhausted, so we stop processing. The output for this example is 5 10. For the final example, we take nums equals 1 2 3 1 2 3 1 2 3. We initialize the heap with the first element from each list, 1 0 0 1 1 0 and 1 2 0. The max underscore value is calculated as max 1 1 1, which equals 1. The heap is 1 0 0 1 1 0 1 2 0. In the first iteration, we pop 1 0 0 from the heap. The smallest value is 1, and the current range is 1 1. Since this is the smallest possible range, we update smallest underscore range to 1 1. Next, we push 2 0 1 into the heap, the next element from list 0. The max underscore value is updated to 2 because max 1 2 equals 2. The heap now contains 1 1 0 1 2 0 2 0 1. In subsequent iterations, we continue processing the smallest elements, updating the range, and pushing the next elements into the heap. For example, when we pop 1 1 0, the range remains 1 1, and we push 2 1 1 from list 1. This process continues until all elements are processed. The key observations here are that the min heap allows us to efficiently access the smallest element, while max underscore value ensures we maintain the largest element in the current range. Once any list is exhausted, we stop since it's no longer possible to form a valid range covering all lists. For this example, the final output is 1 1. Here, we focus on the time complexity of our optimized solution. The process begins with heap initialization. Since we have k lists, we iterate through each list and push its first element into the min heap. The heap, at any point during initialization, contains at most k elements, and each heap push operation takes O log k time. Multiplying this by the k iterations gives us a total of O k asterisk log k time for this step. Next, we have the heap operations during the main processing loop. For every element in the lists, we perform a heap pop to extract the smallest value, followed by a heap push to add the next element from the same list. Each of these operations also takes O log k time, and since we process a total of n elements, where n is the sum of all elements across the lists, the total time for heap operations becomes O n asterisk log k. Now, let's consider the time spent updating the range. For each element processed, we check if the current range is smaller than the previously recorded smallest range, which involves a constant time comparison. Since this happens for each of the n elements, the total time for range updates is O n. Combining all these steps, the overall time complexity can be expressed as O k asterisk log k plus O n asterisk log k plus O n, which simplifies to O n asterisk log k. In terms of space complexity, the heap dominates the memory usage, as it stores at most k elements at any given time. This results in a space complexity of O k. Additional variables such as max underscore value and smallest underscore range use constant space, or O1, and do not affect the overall complexity. The overall space complexity, therefore, is O(k), driven primarily by the heap. When comparing this to a naive approach, the difference is significant. A naive solution would involve generating all possible ranges that contain at least one element from each list. This approach would require iterating through all combinations of elements, leading to an exponential time complexity of O n to the power of k, which becomes impractical as the number of lists increases. In contrast, the heap-based approach we use reduces the time complexity to O n asterisk log k by efficiently maintaining the smallest range with the help of the min heap. This optimized process ensures that we iterate through the elements only once, making it far more efficient. When analyzing the best, average, and worst cases, the time complexity remains consistent at O n asterisk log k across all scenarios. In the best case, where all lists have equal lengths and their elements are closely spaced, we still need to process every element and perform heap operations. Similarly, in the worst case, where the lists have unequal lengths or the elements are spread far apart, the complexity remains the same because it is determined by the total number of elements and the heap size, not the distribution of values. To summarize, the time complexity of this optimized approach is O n asterisk log k, and the space complexity is O k. This makes it highly efficient compared to a naive approach, as it ensures the smallest range is found with minimal computational overhead. When tackling this problem, there are several common mistakes to watch out for. First, many solutions assume that the input lists are of equal length. This can lead to failures when dealing with edge cases, such as one list containing a single element while others are much larger. It's important to test your solution against these scenarios to ensure it works for all inputs. Additionally, some approaches fail to leverage the fact that the lists are already sorted. Ignoring this property often results in inefficient brute force solutions, which are not practical for larger inputs. Instead, methods like a sliding window or a priority queue can help you compute the range much more efficiently. Another frequent mistake is failing to update the range correctly. For every new range, left, right, you compute, you must compare its size with the smallest range found so far and update accordingly. Finally, using the wrong data structure to track the smallest elements can slow down your solution. Instead of lists or arrays, which are less efficient, a priority queue or min-heap allows you to retrieve the smallest element in logarithmic time, which is crucial for maintaining optimal performance. Now, let's explore additional pitfalls and key insights for interviews. One major oversight is missing edge cases, such as when all lists have the same elements or significant overlap. For example, if every list contains the value x, the range becomes trivial, like x, x. Handling these cases gracefully is essential. From an interview perspective, this problem tests your ability to recognize patterns in common problems, such as merging sorted lists or finding intersections. A key takeaway is the use of an optimal data structure, specifically a min-heap, to maintain efficiency. Understanding heap operations like insertion and extraction is something interviewers often focus on. Furthermore, you should be ready to discuss edge cases clearly, like handling lists of unequal lengths, empty lists, or overlapping ranges. Lastly, be prepared to analyze the time complexity. The optimal solution here operates in O, n log k, where n is the total number of elements across all lists. This is significantly better than brute force approaches, and you should be able to explain why this complexity is achievable and necessary for larger inputs. This problem also shares similarities with several other challenges on LeetCode, making it a great opportunity to build transferable skills. For instance, LeetCode 23, Merge K-Sorted Lists, uses a similar heap-based approach for merging multiple sorted lists efficiently. LeetCode 295, Find Median from DataStream, involves managing dynamic data with heaps, which can help reinforce your understanding of heap operations. Another related problem is LeetCode 378, KTH smallest element in a sorted matrix, where heaps are used for matrix traversal. Lastly, LeetCode 373, Find K-Pairs with smallest sums, combines elements from two lists to achieve optimal results. These problems all emphasize the use of heaps or similar data structures to efficiently manage and process sorted data, so mastering one can help build a foundation for solving the others. Finally, let's consider some alternative approaches to solving this problem and the trade-offs they involve. One variation uses a sliding window with two pointers to maintain the range. While this can work, it becomes less intuitive and harder to implement when dealing with more than two lists, making it less flexible for k greater than 2. Another option is brute force, where you generate all possible ranges by combining one element from each list and then select the smallest range. While this is simple to understand, it's highly inefficient with a time complexity of O, n to the power of k, making it impractical for larger inputs. A more advanced but less common approach is using binary search to determine the smallest range. This method is more complex and requires a deep understanding of binary search principles, which can make it harder to explain in an interview setting. Each approach has its strengths and weaknesses, but the heap-based solution remains the most efficient and widely applicable for this specific problem. Great job! To summarize, this problem is a fantastic example of applying heap-based approaches to efficiently solve range-related challenges. Remember the importance of understanding both time and space complexity for such problems. Thank you for tuning in, and I encourage you to keep practicing and exploring similar problems. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!